Okay, so thanks for coming to LLVM social number 6. First of all, I want to put a disclaimer that this talk was created in less than 24 hours. Complete exprompt, and the reason was that Alexei contacted a number of LLVM developers in Berlin, but most of them turned out to be busy. They responded like, we don't have time, maybe later. And basically, we decided to craft this talk just one last day. Yeah, so I'm going to talk about how we implemented the first working proof of concept for Rust programming language in Mull. Couple of words about myself. My daily job is iOS developer and Uber core engineering. I'm a music XML guy there. We teach people how to play guitar. In my spare time, I do LLVM programming. It's almost 1 year. Yeah, basically it's all centered around Mull project. My interests are code quality and testing, and yeah. So what is mutation testing? It's a technique of software testing. It's based on controlled fault injection. We modify code on purpose. It can be seen as simulation of mistakes that programmers often do. It can be seen as a simulation of mistakes that happen in the real world. It can be misuse of software or some hardware errors, or like, yeah. This can be seen as unit testing on steroids. So I see it every day that programmers design their tests only for green cases and at most of the most well-known red edge case, but a lot of code is not covered. With mutation testing, we have a lot more of feedback about how our good tests are. And to give examples of what actually mutations are, we see that there is test. It asserts something, and we have source code. It says that sum is a plus b, and a couple of examples of possible mutations. We replace plus with multiplication, or we replace plus with subtraction. So the algorithm is the following. We run tests in a clean state to make sure that they pass. Then we mutate program and run tests again. If tests fail, it means that our test is able to detect a mutation. If test still passes, it means that our tests are not able to detect mutations. And here I'm giving an example of a shallow test. So basically, on the previous slide, of course, this test could be written better. It could explicitly assert that sum of, that's a mistake in my slide, but yeah, that sum of 5 and 10 is 15. This is not a full introduction to mutation testing. Alexei has spoken about it already, so full introduction you can find his false damn talk. What is Mull? Mull is a mutation testing system based on top of LLVM. The great thing is that it potentially can work with any programming language that compiles to LLVM IR. We already implemented C++ and Google tests. Alexei was a first implementer. Basically, he did a great work of reverse engineering how Google tests how they are structured internally. Basically, he was able to run these tests using LLVM org JIT. And now I'm doing a very similar thing about Rust. So the details are coming. We have one developer that is willing to implement the support for Catch framework, also for C++. I have made very good progress on understanding how to make a support for Objective-C, but it's not ready yet on Apple side. Basically, LLVM JIT is not able to run Objective-C code. There are some problems with linkers and loaders. Swift seems to be very easy to implement. It is just that we don't have time. It's our hobby project, that's why we just don't have enough of hands. But a proof of concept that I made for Swift seems to be that if we take Swift in isolation from Objective-C, we don't try to support Objective-C runtime and Objective-C code, Swift should work with this new exe test framework, which is not Objective-C based. This is a very promising thing for iOS communities, so that actually all iOS developers could get mutation testing for free in a way. Yeah, so to make Mull support a programming language, obviously language must be LLVM friendly. Mainly it should support compilation to LLVM IR. For Mull we are interested in BC code files, bit code files, and LL, which is readable human assembly. We need to find tests, and with each programming language, with each testing framework for that programming language, we have to dive into its implementation detail. Basically, for every framework, for every programming language, we need to do quite big work of reverse engineering how this stuff actually works. Once we can find tests, we can find testees. So basically, we find tests. In every test, we traverse LLVM IR and we look for testees, the call instructions or some other instructions that point to this code that is tested. And we find mutation points in them. Then we mutate this code, mutate mutation points, and run test again, mutated code with LLVM JIT. The great news is that Rust is LLVM friendly. Current Rust is working against 3.9, but people are actively working on LLVM 4.0. I also tried to make a proof concept with Haskell, and it turned out to be 3.7, and also it had some differences from C, Rust or Swift that make it a bit harder to reverse engineer and implement. So Rust is similar to C and C++. It has main function. The first thing I did to actually test it is just li hello world example, and it was very easy to do. Rust does not have a sophisticated runtime magic. It means that if we can find some function in LLVM IR, we can call it. There is no tricky dispatch, it just works. And this is great because yeah, it makes things much easier. Yeah, we had to roll back to 3.9 because Rust does not support it yet, and also because LLVM 4 has backward incompatible changes in LLVM IR. Basically, Apple broke some things, and in 4.0 mostly it is related to debug information. So second thing is compared to the amount of exercises that Alexei and I do about CMake, Ninja compilation databases, and processing these commands using some AVC bloody magic. Cargo just gives us clean commands that allow us to produce this BBC code, and it also makes things very smooth. So once we got this proof of concept working, we decided to ask both LLVM communities and Rust communities. Maybe we could get some hints on how to find these tests in a smart way. Basically, it took a while. We did not receive any answer, but as you see, one guy on Stack Overflow said, with a great amount of Rust reputation, he said that I don't know how to do it, but having mutation testing in Rust would be awesome, and maybe it's even better than to actually get an answer because we can figure it out ourselves. On Rust community, we got answer of Nagisa, and he said exactly what we were going to do. Basically, we just use brute force search through LLVM IR, look through this bit code and find tests somehow. And also he mentioned that we can have problems with optimizations that Rust does, but so far we didn't have such problems. I'll talk about it later a bit. Yeah, so this is where it gets interesting. Basically, we did a bit of reverse engineering. We generated LLVM readable assembly, LL file, prettified it using hands, just made structures, functions, all the layout a bit more readable for humans. And it turned out that the flow is essentially the following. That we have entry point, it's main function. It calls this method, which takes another test main function as a callback and gets these arguments. Later, it does some magic about registration of new thread, doing some other registrations, and it calls back this test main static, which is just given a pointer to a global variable, which only has pointers to test functions and their names. So as simple as this. So basically, when we implemented this, and when this was implemented, we were able to actually find tests. Just LLVM IR, traversing through this file, finding function pointers, and we started looking at tests. Basically, what tests we actually can find, and then we also started to see at mutation points that were produced. And these are three things that currently are producing the most of the noise. By noise, we mean that these mutations produce some information that we cannot deal with as humans. Basically, in source code, it can be, for example, plus, that we mutate to a minus, but under the hood, it has a bunch of machine instructions, and if we mutate them, we no longer can trace the roots to mutation in original source code. That's why we just ignore them to reduce amount of test report. Because with this stuff, it is a lot of mutations which we cannot produce as humans. Maybe it's a great topic for some research in academia, how to actually deal with this stuff. But currently we try to extremely simplify things and only produce reports about stuff that human can actually trace to sources. So this is a C++ example. What we do, it's very dumb. Basically, I want to point out, first of all, we don't generate mutations for instructions that don't have metadata. Basically, this method helps us to check if an instruction has associated debug information. Another thing is that if it does have debug information, but it also contains a link to build bot, it means that a lot of mutations point to Rust sources. And Rust compiler is built on some build farm, on some build bot, and basically we don't have access to that source code because it gets inlined to the code of our tests and testees. So for now we just filter it out, and I previously mentioned that solution can be that we just build Rust from sources on our own, and then this build bot becomes our user directory and we can work with these sources as well. But for now we just filter it out. And another thing is these panic instructions. Basically a lot of calls, Rust is very safe. It means that it panics on every second step. And that's why a lot of mutations contain mutations of panic calls. And as humans, we are not interested in them because it's also a bit of wrapping that Rust does on top of our code. For example, this is what we do in C++ and Google Test. It was the very first filter that Alexei did for include C++ v1. Before we enabled this thing, mutation reports generated a lot of things, of mutations happening in string classes of std, for example. And basically, it does not make sense to work with mutations there, because if we, like our code works with mutated C++ string somewhere, most likely it's a false positive. We cannot get some value out of these kind of mutations. That's why we just dramatically reduce amount of generated reported functions. Yeah, so now we are able to find tests. Now we are going to run them. And again, this is a part of previous slide. We have function mine. It calls std rt start, and it calls back to test mine, which actually runs a method which goes through each test and runs them one by one, and each call to each test is wrapped into a safe exception handling, so that if one test is failing, it gets caught, this exception, and we go further. So basically it's invocation of test one by one wrapped into some safety, so that we catch all exceptions, panics, so that test suite works. It's like sandboxing. Yeah, so one interesting difference between Rust and C++ and Google Test is that if a Google test fails, it just returns, I think, 1. So it returns 0 if it passes.
Number of failing tests.
Yeah, yeah, the idea is that basically Google C++ tests, they don't panic, but just return with some value, correct? And in Rust, it's a bit different, that if assertion fails, it panics. It basically crashes a thread. And that's why we also had to learn about this length start function, that it creates a new thread, wraps tests in an exception handler, waits for the execution, and yeah. For our Mull running purposes, we have to do similar thing, but we do it in a bit different way. We don't run main at all. We don't run test main, but we obviously have to look at it to find pointers to test functions. Then for each test, we create a separate process to sandbox a test that may crash, because if we mutate test, it panics, and then if we run it in the same thread, it will crash the whole test suite. That's why we use fork. And this is exactly the difference between Rust and Google Test, that to consider test as failed or crashed, we have to actually we have to see it crashed. In Google Test, it would be just a normal return of some value. So in Google Test, there are no crashes, unless we break the code doing these mutations. Yeah, then obviously once forked process it passes, parent process of Mull considers an exit code and the signal handlers, and if function just returns without any panics, we consider that test passed. If it crashed, timed out, or basically it crashed or timed out, we consider it as failed. Yeah, so one thing which is also different from Google Test is that there is no plus instruction in Rust. Plus calls, if we say a plus b, it gets translated to arithmetic with overflow intrinsics. Basically, it means that if we have some integer and we get to its bound, to its boundary, and we try to make a +1, Rust panics. It says that you attempted to overflow an integer, and that's why so in Google Test we just replace plus with minus, and it's very easy. We had plus instruction, we replace it with minus, but in this case it's trickier, because summation is represented by a call instruction to LLVM sadd. Basically, it's the full name is like this. And thing that we tried, we just replace LLVM add with overflow with subtraction with overflow. But then we had unexpected things. So we expected that assertion will fail, that some AB will panic because tests will obviously fail. But instead we see that the guard of addition with overflow instruction panics because it does not see the expected result of a summation. And if we look a bit deeper, we see that this call to LLVM uadd with overflow, in context it looks like this. It does something, so this is a call instruction to LLVM uadd with overflow, but then it does some validation. And basically this is where we get this unexpected output, because it is LLVM expect that does not find the expected result of summation. That's why it means that we cannot work with add mutation operator unless we disable compilation options to disable these wrapping checks. Yeah, so we created two libraries, test reports for two libraries. One of them is Rust CD Mongo. It's a very small library, and also we created a second report, but now we are having some crashes there. So basically, in this talk, I'll only show this small library. I'll try to find it, just to show how the final report for mutation testing works. So again, I'll open the second one also. We have two versions of mutation reports. This is a normal one. Basically,
Common Plus,
yes. Yeah, the library is very small, and also we filtered out the noise. So with noise, it's a lot more mutants, but they all point out to some panic instructions, things that I mentioned before. Basically, here we see that we have 8 tests, 8 mutants, and they were all killed. It means that when we did some mutations, they actually, the tests of the library were able to detect this change. So it's a good thing. This is how it looks like in the report. So this is an example of negate mutation operator. We see the tests that started failing once we did this mutation. This is something that we're going to fix with time, that like this caret does not point to correct exact location of where mutation was happened. But we see that it crashed. Distance 1 means that it's a call stack of 1 level depth. It's not probably relevant for now, but this is interesting. This is actually how Rust's test panics when it hits the mutated code. And we see that there is assertion, like left was expected to be right, left was this, right is this, and it failed because of negation. And from here we cannot see where it actually happened. As I said, we have to polish our connection to real debug sources of
I think it's actually the Rust gives us wrong debug information. The information about position in the file always is 0 for
it can be. So we have to investigate this as well. This is the same report, but in debug mode. It's a bit raw version, but also extended one. So in this case, we see the original set of instructions. We always go to the bottom. It's a few, quite a few, and we see that it happened. So it was a comparison instruction. It's this location 36. If we go to 36, we can see that what actually happened. So what was mutated. Does anyone know? Yeah. So this is one. Basically, the way how we analyze it currently is that if we don't see clearly what was mutated in source code, we go to this debug mode and we try to learn what actually happens under the hood. And that's what I mentioned previously by noise, because it's very often that a mutation shows you something in the source code, but then looking at the instructions, you cannot clearly see what is the connection. Sometimes it happens in machine code, but beyond the source code. Yeah, and if we go, just to make it again, the whole thing, if we start scrolling it, it's a lot of mutations that were produced. We filtered out the noise. That's why we always see that it was always panic in assertion failed. When it is noise, it can be some crashes, some things that are even harder to process. Yeah, so yeah, so this was example. We are going to publish it. Something has happened to
errors.
Just a second, maybe I'll just reload the full screen. Yeah. Yeah, so this is our to-dos. It's a lot of work. We do it in spare time, that's why it's just not enough of hands, but basically the first thing, and it's also a great goal for C++ projects, because in C++ there is no easy way to get a compilation database which would produce a bit code directly and easily. There are some tools, but they all more or less approach the same task from different sides, and we did not find any good tool so far that would just allow us to do it easily. It can be some exercises on top of CMake, it can be exercises on top of Ninja, compilation database, and also bloody bash, avk, magic, whatever. So the same problem still stands for Rust. Currently we are only testing embedded tests. So if you know, in Rust there are two groups of tests. First of them are directly embedded to source files, exactly this source group. Another group of tests is actually in tests, and in this case tests are separate from a source code. Currently we're only working with this, and Rust C only produces one file. And if this file, for example, is 5 megabytes, it makes a recompilation very slow. And it means that to generate a report for NOM, it's a Rust parser combinator framework. It takes hours. You can just start a machine, put it on night, and the next morning maybe you will see that results actually were generated. And one of the reasons is that we recompile one big BC file every time. This is because Rust C currently only produces one file. We would like to decompose it on some smaller modules. Obviously, we also have to learn how to generate bitcode from tests. From this group of tests, it's another big task. And I already mentioned about this add mutation operator, that it does not work easily for us because of this add with overflow semantics. Basically, we need to learn how to disable all possible optimizations so that we deal with error code. This is an easy task. Basically, Rust symbol mangling is different from C++. They're similar, but not exactly the same. Probably we can just port this Rust C demangle to C++, and we will get readable output for tests for original methods and source code that is being mutated, and it will make reports readable by humans. This is also very simple task, more mutation operators. Currently we only do add plus with minus, remove void function call. When there is a function that does not return anything, we just remove a call. And it's a great mutation for C++. It found some interesting results. Basically, it's quite often the case in LLVM when you remove some void function and tests still pass. Like nothing happens, all works like all is good. And negate condition. It's like we have if something is true, then do something. We negate and do it. If something is false, then do something. It is also very effective mutation. And many more can be added. We're discussing this with some other authors of mutation testing systems. This is to be done. Obviously, reasonable number of real-world projects have to be analyzed. Now we are getting to we want to have a good readable report for GNOME, this Rust parser combination framework. And yeah, I'll talk about it a bit later. Obviously, with new mutation operators, some noise will come. It's always the case. Once we implement some new mutation, we have to deal with the noise that is produced, some irrelevant instructions, irrelevant source code, and this has all to be filtered so that we can read it easily. Yeah, so basically these are probably the most interesting questions that are about our strategy. So we want to answer if this mutation testing can actually detect serious errors in the real world programs, because it is a lot of effort, a lot of reports of mutation testing have to be analyzed, and so far I think we can say that we did not find a single serious error. For example, Alexei analyzed some parts of LLVM code. We found some trivial things, like, for example, you do some mutation in string containers, or some remove a string that removes something from a vector, but tests still pass, and knowing that C++ is not a safe language, it's more or less, we cannot consider that this mutation testing reveals something really interesting to us. So that's one thing, that we want to make a tool mature to really find something interesting, because there are articles in academia that claim that mutation testing, when it is implemented properly, it can actually detect very serious errors that happen in a real world software, also hardware errors. It makes a software much more robust. This is also a topic for research. A lot of researchers in academia, they research on what is, for example, the most minimal combination of mutation operators that can yield the best results, and to cover all other mutations. So that's a great separate topic of research. Obviously, we have to compare mutation testing with other methods like static analysis, fast testing, and decide and see which method is more effective, or maybe which method is more effective for particular groups of problems, and etc. And this is ongoing discussions. We discussed this with Olivier, we discussed it with Alexei. Basically, is mutation testing specific? Obviously, it can help to find unreachable branches, for example, or easily detect some unreachable code. But the question is, can we have some mutation operators or combinations of them that will reveal something really interesting? So these are the links. This is a project itself. This is Alexei's talk at FOSDEM. It's more detailed than what I'm talking about now. And there is interesting article where people actually made a research on, they inspected some big code databases, and they make some claims that it is actually possible to detect real faults with mutation testing where the tool is mature. In our case, we are very far from there because it's a lot of work. Compilation pipeline is not ready, mutation operators are not implemented fully, so this is something that we have to answer. Questions?
So those 8 mutants, how long did it take to test them?
8 is very fast. It's maybe, I think it's 15 seconds roughly, 20 seconds.
Per mutant? No.
Full thing.
Oh.
But later, when the most time-consuming thing is a compilation of modules and mutated modules. And once we compile them, we write them to cache. So if you run the same thing second time, it is very fast, and it is very fast even for big projects. As I said, for Rust, it's very critical that we find some way to modularize BC code, so that we mutate small pieces and recompile small pieces every time. So for small projects, it's very fast, and yeah.
So why did you limit to 8 mutants?
We did not. It's how it's what I mean. It's just a few tests.
Because there was only so many adds and if condition. Oh.
So the thing is that this Rust C debugger, as I mentioned, Rust has 2 groups of tests. In embedded tests in library, we're only testing them. I think it's only 8 tests there, small number. But there is also tests folder, and there are a lot of tests, but we didn't get to it yet. That's why in this case it's just a small library. That's why we only have 8. And it's 8 mutations that we found. For example, if we would have more mutation operators, this number would grow.
So because there was only 8 plus or 8 void function call.
Yeah.
For GNOME there was 2,999 mutants for another library.
Yeah, and in one method it was 160 mutations. So it is probably a long method, and even these 3 mutation operators like add, remove, void call, and negate, they found 160 mutations. It means that for each of these 160, the whole thing has to be run.
So I have a more basic question, I guess. So I'm not sure yet. So in the first, it seemed to me that the idea was to figure out how good your tests are, because if you are able to make a mutation and your tests still pass, that means you do not cover something, because
exactly it means that your tests are shallow or it's not enough of them.
Yeah, so that seems to be one use case, but now it seems like that there's also a use case that you can actually so this is, let me just summarize. So this is, you find let's say a bug in your tests. Let's call it a bug. And now it seems that you also want to be able figure out bugs in the actual source code. I mean, not the tests, but in the source code. And that is what I don't get. So this somehow assumes that your tests are well done, and now you actually change something in the source code, and now I don't know actually. So this is kind of my question. So you see, it seems to me that a second part is to detect defects in the software, not in the tests, in the software. Is that kind of is that able, or do you want to do that? Or do you get my question?
Yeah, so I can probably answer it. So the paper that Stan mentioned, that claims the paper claims that they were able to find 70% of real faults. So the researchers, they took don't remember exact number, but 500 or 300 they found 500 or 300 of real bugs in software, and then they found a commit that fixed those bugs, and run mutation testing against the system right before that commit. right before the bug fix.
Mm-hmm.
And they found that mutation testing shown that the test was not good, was not exhaustive. And if you add more tests, then you would catch that bug.
I see.
So this is where like this idea comes from.
That makes sense. I see.
Yeah.
That's quite interesting.
It makes sense, but it is also a lot of research because one has to analyze these huge reports. That's why we extremely filter out the noise.
Mm-hmm. So this is something I wasn't. So it seems to me that the approach was like it sees all of the source code and then you're filtering out specific stuff. And I was like, so why don't you go the other way around and say, you know, only include me sources that are like what I care about. So I remember the C++ example where you like excluded like standard C++ library stuff, and I was like, you know, if I'm testing, let's say, my project, and you know, I don't care about bugs in the standard library, maybe I should, but I don't, and so I just want only my my thing to be tested, meaning there should be no mutations in like third-party libraries.
Yes.
Yeah. So this is what so it seemed to me like you are like, you know, you see everything, and now you're like excluding this, and that, and I was like, so why don't you just say, you know, only include my sources?
Yeah, but again, I will jump in. So
of course,
in case of C++, and I think the same goes for Rust, you have your function, your code. But after on the BC, on the bitcode level, C++, like some code is being inlined already.
Yeah.
So your function, like it's not your function anymore. You may have just like I saw it. You have just one line of code, like one function with the one line of code, some vector push back something, and it actually gets like 700 lines of code. So
true. It's different. It's difficult to draw this distinction.
At least for C++.
Yeah, and I actually did not mention it that Rust also has macroses, and these macroses are in a way similar to preprocessing in C++. It means that a lot of mutations can be generated out of those macroses, but we will not be able to exactly trace the original source code where it happened, because they get expanded. But that's fine. So, no more questions. So, thank you everyone. And thanks for this co-working place. It's, I think, the fourth event that we're hosting here.
Yeah.
Thanks to these guys. They're very friendly.
Go.